Hello there. In our last review section 1.4 in chapter 1, before we can get to the calc stuff, we're going to just review functions. So a function is a particular thing in mathematics, and it is something that we've kind of seen before. I mean, I've tried to been calling them equations, but a function is something that looks like an equation, except with one thing that we need to make sure of. So a function is a rule, so it has a formula, in other words, but it's a rule that has a particular thing. So it's a rule that assigns exactly one output to each input. So exactly one is the key thing here. We want to work with functions because if you think about what would happen if you put in an input into something, so think like an X value, and you could get two answers out. That would be really hard to work with, right? So functions are really nice. And it's basically just us saying, okay, we want to work with functions only so that when we have one input, we know that there's only one output that comes out and there's no like ambiguity about that. Okay, the notation that we're going to use for a function is one that you should have seen before. So normally we use a lowercase f for function. So the notation for function looks like this. We put f, and then in parentheses, we put the input variable. So that could be anything. Normally it's x. And then we say this equals the output, formula for the output. Now I know that we often use parentheses like this to indicate multiplication, but this is not multiplication in this case. Okay, so this is not multiply. We have to be aware of the different contexts that we are using symbols in math, and that is one of the hard things. And the way that we would read this, we would say this, it's f of whatever the variable is. Okay, so if we were going to use our standard variables, which are x and y, x for our input, and then we would have a formula over here, but normally we use y as the output. Okay, what we would say, like how we would read this, is we would say f of x equals, and then there'll be a formula over here with x in it usually, but in this case we can just say f of x equals y. That's how we would read that. Okay, again, we do not have multiplication here. This is called function notation. And we want to be able to use this because it's really nice. Right, the purpose of it, again, is to indicate what is the input variable. Sometimes we'll have more than one letter over here. And so this tells us what the variable is in maybe something that's got more than just x over here. Okay, so for example, we were looking at lots of things and we were writing them as y equals. So this whole time so far in this class, we've been writing things as y equals. So like y equals 1 minus x squared. This is an equation. Not all equations are functions. In this case, if you think about plugging in one x value into here, you will only get one number out. Like there's no possible way to get more than one answer out. Okay, so we would write this in function notation. So this can be written in function notation by just replacing the y with f of x. Okay, so y equals 1 minus x squared is the same thing as saying f of x equals 1 minus x squared. Now, not all equations, okay, equation here, not all equations are functions. you might remember the vertical line test. Okay, so this is just a little bit of an aside. Not all equations are functions. For example, the equation for a circle, x squared plus y squared equals r squared. This is an equation. It's fine. You can write it down. It has a graph, right? It's a circle when you graph it. This is a circle centered at the origin with a radius of r. But when the graph is a little maybe easier to see this. When you choose an input value, so say we choose an x value along the x-axis, so say we choose this x value here. We would read off the output by finding where the y value is on the curve. So there's a y value that goes with that x value here, but there's another one down here, right? So we have two outputs for one input. And so that means that this is not a function. Okay, so again, if we have an x value we're choosing here, this has two outputs or two y values. Okay, so of course it doesn't happen at every x value, right? We have one right here. This just has one y value there, or one output. But for most x values here, this will have more than one y value or output for a given x value. So this is not a function. Okay, you might remember again the vertical line test. So if you draw a vertical line, it's kind of just a shortcut for you to see, is there more than one output? So we could say fails the vertical line test. This is kind of why the vertical line test is a thing, or why it works. Okay, one more example. We can use more than just f. Like if we're talking about more than one function, we might call a second function like g of x, or h of x, or whatever, any letter that we want, basically. So if we say v of t, that means that we're calling the function v, and then in parentheses, this is saying that t, that's the variable that is going to be changing in our equation. That's going to come after the equal sign. So if we say v of t is equal to CR t squared, well, there's a lot of letters over here on the right-hand side, right? We have C, we have R, we have T. So this notation is really nice because what this says is, in particular, this part here with the V of T, okay, this tells us that the variable is T. That's what's going to be changing. If we want to plug something in, that's where we'll plug it in. And then C and R, we refer to these as constants. They're not variables. We're not considering them as being changeable. They are things that are staying the same. They might represent some kind of constants like in, I don't know, in science, like the speed of light or something like that, like in E equals mc squared, right? So something along those lines, constants like that. Okay, so another really cool thing about function notation is that when you are plugging something in, like another input into a function, the notation is really nice and condensed and very clear about what's going on. So let's take a little bit of time to review evaluating functions. So here we've got a quadratic f of x equals x squared plus 3x minus 5, and we're going to evaluate the function at various inputs. Now basically what this means, when you evaluate a function, you're just substituting in or plugging in for x, is all this means. Okay, so x is a placeholder for whatever input that we have. So that's the whole thing here. We have x here. Whatever we're going to input in, we're going to put it in here for x and in here for x. It's in two different places. So if we plug a 3 into here, right, this is going to look like, okay, well, we're going to take 3 and plug it in for x. We have 3 squared plus 3 times 3, and then minus 5. Okay, so figuring out what this number is, 3 squared is 9, 3 times 3 is 9, and so this is 18 minus 5, which is 13. And so there's the output associated with the x value or the input of 3. Now, like we reviewed in the previous few sections, when you plug in an x value into an equation, you get the y value out that goes with it. So this still applies here. So still 3 comma 13, right? X was 3, f of 3 is 13. This is still a y value here. So 3 comma 13 is still a point on the graph of f of x. That is all still true. So this still just means y value as well. Okay, f of -2. So here we're just going to plug in -2. We have to be really careful with parentheses when we're squaring stuff. So -2 squared. Okay, if we write it like this, we would square the 2 first. This would give us 4, and then we would negate. So this would actually be -4, but that's not what we want to do. We want to actually square the whole input, which is -2. So we need parentheses around the -2 here. Okay, then we'll add 3 times -2, and then we subtract 5. Okay, so -2 squared is 4. 3 times -2 is -6. We've got 4 minus 6, which is -2, and -2 minus 5, which is -7. Okay, so again, the point -2, comma, -7 would be a point on the graph of the curve, the parabola, if we were to graph it. Okay, we can also plug in like other variables. So if we wanted to figure out what f of a was, okay, we're just kind of plugging in a for x. All right, so instead of x squared, we'll have a squared. Instead of plus 3x, we'll have plus 3a. Instead of minus 5, well, that'll stay the same, right? There's no variable part to that. Maybe I'll highlight our answers here so that we know we're done. All right, f of star, we can plug in, I don't know how meaningful this is, but f of star, we could just plug that in for x. Okay, everywhere that we have an x, we're gonna plug in a star. So we'll get star squared, plus 3 times star, and then minus 5. I don't know, nothing really to do to simplify this at all, because how would you? So there is f of star. So I hope you're getting the idea, right? It's just the placeholder for the input, and we just put in whatever we want to plug in into the placeholder of x. The f of cat. Okay, well, same thing. We're going to square cat, so parentheses around the cat, because CAT, even if we were plugging in C times A times T, we would still need all these parentheses here. So cat squared plus 3 times cat, and then minus 5. And I don't know how to simplify that, so we will leave it just like that. Okay, now it always trips people up a little bit when we have something like the next couple examples, where what's being plugged in is like x plus something, or x minus something, something with like a plus or a minus in there. The process is exactly the same. It just is confusing, and I get that. I get that it's confusing because we have an x here, right? And there's already an x here. But just remember that whatever lives inside the parentheses, that's what we're going to be putting in into our blue bubbles here for x. Okay, this whole thing, the entirety of x plus 1, I don't care that it's x plus 1, like that's just the thing that's going to be plugged in for x in our equation. So be careful here. This isn't going to be just f of x, which is this parabola or quadratic, and then plus 1. Okay, this is not the same thing. This would be, if we wanted to know what this would be f of x, and then add 1 on the outside. Okay, so be really careful with that. They're very different. So pause this and take a second to write down what you think this will be when you plug in x plus 1 into the function. Just take a try, write down something, see what happens. Okay, so it looks like, well, let's see, taking one step at a time, we've got x squared. Okay, so instead of x, we've got x plus 1. So we're going to square all of x plus 1. Okay, this is just this term here. Oops, just that part here, right? We're plugging in x plus 1 into here, so we just square the whole thing. Then we're going to add 3 times whatever we put in. Okay, we're putting in x plus 1, so it's be plus 3 times x plus 1 in parentheses. And then minus 5, that's just minus 5, right? There's no x or anything there. So that's the first step in, plugging in x plus 1 here. I think we could probably simplify. We'll have some like terms to combine if we were going to expand and then maybe condense. So to simplify this, x plus 1 whole thing squared, that's really x plus 1 times x plus 1. So we're going to have to FOIL that. Okay, be careful here. I know this looks like x squared plus 1, but it's not. We can't distribute the square over the parenthesis. We can, however, distribute the 3 into here, 3 into here, and here. All right, let's FOIL out this product here, x plus 1 times x plus 1. So that'll give us, first is x squared. Outer and inner are each 1x, so that'll be plus 2x. And then last is plus 1. Then we still have plus 3x plus 3 minus 5. And now we can combine some like terms together. So we still, we got only 1x squared, so that'll stay by itself. We've got 2x plus 3x, so that's plus 5x. Then we have some constants. We have plus 1, plus 3, so that's plus 4, and then minus 5, and so that's minus 1. And here we go. Here is the plugged in or evaluated f of x plus 1 for the function. I know that was tough. Let's try something very similar, but a little different. Let's try f of x plus h. Then we can see down here, we're actually going to put this together into something else. So f of x plus h, this is really the same idea as before. So again, why don't you pause this? And having gone through example 6, maybe this will help with example 7. Okay, so we're going to plug in x plus h, the whole thing in the blue blob there, in for x. So we're going to square x plus h. Okay, that's the first term. Then we're going to add 3 times x plus h, that's the second term. So plus 3 times x plus h. And then we still have minus 5. Now to simplify this, the process that we're going to do is going to be the same. We'll expand out and see if there are going to be any like terms that we might be able to combine together. Maybe there will be, maybe there won't. I don't know. Let's see. So we're going to have to, if it helps, maybe we can write this as x plus h times x plus h. Okay, let's distribute the 3 here. And then again, we're going to have to FOIL out this product of those 2 binomials, 2 things with 2 terms in them. So we're going to get our first term of x squared. Our outer term will be x times h. So in outer, these 2 multiplying. our inner terms multiplied will be h times x, but that's the same as x times h. So we're going to have 2x times h's. And then our last, that's what the L means in FOIL, right? So the last h times h, that's h squared. And then we've got plus 3x plus 3h minus 5. I don't see any like terms that we could combine together. Okay, if they're going to be like terms, they have to have the same variables to the same power. And I don't see anything like that, so it looks like this is our simplified form. Okay, example number 8 is a combination of a couple different function evaluations, and then it's got this divided by h in the bottom here. Well, this whole thing here is actually a pretty important thing that I'm going to tell you all about in chapter 2. For now, it has a special name, and it is called the difference quotient. But it's got a huge meaning behind it. We just have to wait a little bit to see. It's actually a very foundational calculus thing. But for now, we're just going to practice, our function notation and function evaluation and our algebra to simplify something like this. And then we'll build on it a little bit later. Okay, so it's a difference. You've got a minus here, and it's a quotient. You've got it divided by, so I don't know if that's why it's called that. So basically, there are 3 pieces that we have to find in order to figure out what this is. Like in my mind, I'm chunking this into 3 parts. So we've got this part, f of x plus h. Well, we found that already, right? That's up here, so that's nice. Then we've got this part here, f of x. It's actually nothing to do with that. Like that's just the function that we are given in the beginning. And then we've got this third part here, which is h. Well, I'll tell you what the h represents soon. For now, we'll just think of it as another constant in this case. Okay, so let's see. Let's go looking at the first bit first. So let's look at f of x plus h. So we already found that. Okay, so f of x plus h, just so we're all on the same page here, that's what we found in problem 7. So this is x squared plus 2xh plus h squared plus 3x plus 3h minus 5. I encourage you to maybe pause this and try it again, just so that you can make sure that you're kind of okay with this for now. Okay, the other part that we have here is f of x. All right, well, that is just the function, again, that we were given. So what is that up here? It was x squared, okay, right here, x squared plus 3x minus 5. X squared plus 3x minus 5. And like I said, h just stays as h. So what we have here, okay, it's going to be the pink stuff. All right, so let's see. Pink stuff is x squared plus 2xh plus h squared plus 3x plus 3h minus 5. Then we're subtracting. Okay, so I have minus, a big minus in the numerator of the difference quotient. Then we have the green part, just f of x. So that's all of this stuff. Now you may remember when we were working with finding the profit equation, when we were subtracting cost, cost had more than one term in it, so we needed parentheses. The same thing is necessary here. So the way that I've written it, the minus is only connected to the x squared, but we want to subtract the entire thing here, so we need parentheses around the f of x part. And then this is all divided by h. This looks crazy, right? Normally, these kinds of things simplify a whole lot. You just kind of have to take it step by step. So This is the difference quotient. We wrote this down for our particular function. Okay, so this is a formula or something that can be found that will be different depending on what f of x is. Okay, this is the difference quotient, not fully simplified yet, for this function here. But again, it will be different depending on the function that you have. And we'll do 2 more examples with this just in a moment. Okay, so from here on out, we're just going to simplify. So the first thing I would say to do is to distribute the negative sign, because then we'll be able to maybe cancel some stuff out or maybe combine some like terms. All right, so let's go. Pink stuff, not touching that at the moment. Green stuff though, that's going to change the sign. So we'll have minus x squared, minus 3x, and then plus 5. And then that is all divided by h. And then taking a closer look, it looks like we've got a lot of things that are just going to add up to 0. Right? We have x squared and negative x squared. Those add up to 0. We've got minus 3x and positive 3x, so those add up to 0. We've got negative 5, minus 5, plus 5, so those add up to 0. And so what we're left with here in the numerator is just 2xh plus h squared plus 3h. Now, I know that it's very tempting to look at this h down here and just kind of remove it with maybe that one, or maybe you want to cancel that there, or maybe you just want to get rid of that one. Please don't do that. Remember that when you have things in the numerator separated by plus or minus, you have to remember that this is being divided by h, this is being divided by h, and also that is being divided by h. So a thing that I would highly recommend that you make a habit of doing is always factor out the numerator as far as possible, and then you can see if then you can cancel with something in the denominator. Right, so in this case, we can actually factor out an h from the top. If we do that, we'll get 2x plus h to the first plus 3. And now in the top, we have h times something. Then we are dividing by h. And so here, we absolutely can cancel these. This is a really important step that we will always need to do. Again, when we get to talk about the purpose and the use for this. Okay, this is a crucial step for canceling or simplifying a difference quotient, is canceling out that h there. Okay, what we're left with here is just 2x plus h plus 3. And this is the simplified difference quotient. Okay, so just to summarize here, okay, you've got, this is a tough thing for a lot of people. So to kind of give you some general steps here, the first thing you want to do when you're finding a difference quotient is to write it down. Like write down the difference quotient or for your function. In other words, find f of x plus h, find f of x, that's easy, and then like form it, like make the first step by forming it in this fraction. Then what you want to do is work on possibly simplifying the numerator. And there's going to be a couple different ways that we do this, actually maybe 3 different ways. One way is to do what we did here, where we expanded out the numerator, maybe distributed a negative, and then we canceled some like terms. You'll see 2 other ways that we will simplify in just a couple minutes. Okay, then lastly, this step here is super important. The third thing that you always want to make sure that happens in your difference quotients is that you'll be able to cancel an H in the top and in the bottom. That's basically when you know that you're almost done. And again, we'll see why that H canceling is super, super helpful and what that means in the very near future.